look how beautiful that is. All those colours. Absolutely breathtaking. And the sellotape doesn't have any colours usually, but wow, look at that. This is a laptop screen, just a laptop screen panel that's emitting nothing but white light. And this sort of LCD screen produces polarized light. What does that mean? The light's coming towards your eye from this panel, and if the light was unpolarized, the electric field would be shaking this way, be shaking every way. Remember that light is an electromagnetic wave, and we're only interested in the electric field part of that. So the electric field would be shaking in all directions. Now, this is polarized, which means that the electric field's only shaking in one particular direction. I don't know what that is. With some laptop screens, it's vertical, some it's horizontal, some it's diagonal. I'm going to assume, for simplicity, that in this monitor, it is vertically polarized, which means that all the light that's arriving at the camera has electric field oscillating vertically. This is a polarizing filter. And right now, it's set up so that it only allows light with a polarization direction that's vertical to be transmitted. Any light that has a polarization direction horizontal is absorbed by this particular polarizing filter. Sometimes they're called Polaroids, but I think that's a trade name or a brand name or something. Now, if I rotate this, so remember the polarization direction is vertical, if I rotate this around, watch what happens. Well, now we're only letting light with a polarization that's horizontal through, and there isn't any because the laptop screen produces vertically plane polarized light. And what we could do is we could set this up. So that's at 0 degrees, the polarization direction of the filter and the polarization of the light from the screen are in the same direction. This one, it's a bit scuffed there, but it'll work. Tilt it a few degrees. Let's take another one. I've got loads of these things, so pop it there, tilt it a few more degrees. This one, put it there, tilt it a few more degrees still. And you can see what's happening is as I tilt them further and further and further around, let's move these along a bit, as I tilt them further and further and further around, they absorb more and more light until eventually they're absorbing all of it. So we need to understand how this works, and that leads me on to a little presentation. Let's imagine that this is the z-axis. This is the axis pointing straight towards you. And we have light that is polarized in the vertical direction, which means the electric field is oscillating vertically. The maximum electric field strength is going to be the amplitude. So that I've labeled that A0. A0 is the amplitude of the light emitted from this screen. Fine, okay. There's my filter. Let's get one that's not scuffed so badly. There's my filter, and let's imagine that I rotate the filter to, let's say, 45 degrees. So what happens then? Well, at 45 degrees, which is about that, that's the direction of the, there we are, that's the direction of the filter. It will allow light to be transmitted if the electric field is shaking in that direction. And you're going to say, well, hang on a minute, the screen's producing light that's has an electric field oscillating vertically. This is diagonal, it's not vertical. Well, correct. But there is a component of that electric field which is parallel to the polarizing filter's direction of polarization. So here we have the green dotted line, which is the direction that the polarizing filter will allow to be transmitted. And you can see that we can resolve how much of A0 is along that direction. These are right-angled triangles, so there's A0. That's a right-angled triangle. So this bit here, which we call A1, that is a component of A0, one of the perpendicular components of A0. And we calculate it by using A0 multiplied by cosine of the angle between the vertical and that diagonal, which I'm saying is 45 degrees, so this will be about 70%. Okay, fine. That's how polarization works. No big deal. But watch this. If I take my filter and I put it at 90 degrees, Cosine of 90 is 0, so nothing gets through. I take another filter. Let's get one that isn't quite so scuffed. I take another filter and I place it here. Notice it doesn't do anything. Obviously, the filter that I'm holding in my right hand is a second filter, which is between the first filter and your eye. And any light that passes from the screen through the second filter straight to your eye is affected just as it was when I rotated the first filter. But the light that is going from the screen through the first filter and then through the second filter is unaffected by the angle of the second filter. But what if instead I rotate the first filter? Now that's very interesting. You should find that very interesting. So it's light from the screen passing through this filter, then through this filter, then to your eye. I keep calling them filters. They're polarizing filters. Okay, so that's interesting because no light is getting through there because this is vertically polarized light from the screen and this polarizing filter is only allowing horizontally polarized light to be transmitted. And there isn't any because it's all vertical. But if I place another filter in between the screen, the source of the vertically polarized light, and the second filter, at 45 degrees, or some angle, then some light does get through. Now this needs an explanation. So what's happening here? Well, here I have my first filter, which is at 45 degrees. We can see that here. That's what's happening at the moment. The first filter, that's the filter on the left here, is doing exactly what our equation said. And then we have a second filter with its direction of polarization orientated 90 degrees to the screen's polarization direction. Okay, fine. But the light that reaches the second filter has already passed through the first. So we're actually resolving the light from, let's move that down here, we're actually resolving the light from the first, come on, that'll do, the light from the first, that's got through the first filter, then resolving that in the direction of the second filter. And we can call the angle between the green and the blue arrows theta 2, and so there we go. That's the angle that filter 2 makes compared to filter 1. Theta 1 is the angle filter 1 makes compared to the plane of polarization of the light from the screen. So, and again, I keep calling them filters because that's what they're doing. They're absorbing some of the light and allowing the transmission of others. So I think it's okay to call them filters. So that's what's happening. A2, that's the amplitude that gets through both filters, is now equal to A1 cosine theta 2. And because A1 is A0 cosine theta 1, we can substitute that in and we get this expression here. So light does get through. And if these angles are both 45 degrees, we get about 70% of the amplitude getting through. So 70%, 70%, we're getting around about half of the amplitude actually getting through and being rotated around in those steps. Wow, that's exciting. But what does that mean for brightness? Well, let's just talk about intensity for a second. Oh yes, I also have this demonstration that there's no component of that along this direction, which is why I get no light passing through this part of the filter on the right. But no, this is the relationship between amplitude and intensity. The square of the amplitude is proportional to the intensity, so the square of the ratio of amplitudes is going to be equal to the ratio of intensities. Those are I's. Fine, okay. So what's that got to do with the exciting thing you saw at the start? At the start, what you saw was a piece of sellotape in the middle of the screen, and we've got polarized light, plain polarized light passing through the sellotape. And when I take a polarizing filter and I place it between the sellotape and your eyes, we can see beautiful colors, just like that. That's interesting. That should be explained. We should be able to explain why that's happening. And that's what I plan to do. So the sellotape is birefringent. Sometimes I've seen it or heard it pronounced birefringent. It's birefringent. And there's actually quite a lot of materials that are. So here is a lid from some takeaway food, and yes, that's also birefringence. If I take the filter and put it like this, you can see, look at those beautiful colours. Absolutely breathtaking. Where the colours change more quickly actually indicates there's a higher stress at that point, intrinsic stress. Or I've got a balance here, just a normal balance, and actually you can actually see some interesting effects there, which I won't go into now because of something called a Brewster angle. But let's ignore that for a second. Let's just pop that down there. And if I take a polarizing filter, just as I had before, and place it like this, isn't that beautiful? And in fact, that was one of the, I'm rotating the filter, as you can tell by the background colors changing. This is one of the effects. In fact, this I think is the reason why I chose to study photonics as my master's at university. Absolutely beautiful. And you can do it with rulers and so on. Let's go get a ruler. Yep, here's a ruler. Shatter resistant. Yeah, don't care. Take a polarizing filter and just look. Absolutely beautiful. How could you not be moved by that? Just rotate the filter around. So, how do we explain what's going on here? Well, the light, remember we go back to here, the light that's passing through this particular material has different speeds depending on the polarization. So it's called a birefringent material because there are two different refractive indices. And the light passes through this, and I can change the angle of this. The light passes through this, and it might be that for a particular part of this, it's a polymer, so it's complicated, but it might be for a particular part of this, the light that's polarized in one direction, let's say vertically, goes a little bit faster than the light that's polarized horizontally, just a little bit. Might be that, or it could be the other way around. And so as I rotate this around, then the light that's orientated in just this direction goes from being a bit slow to being a bit fast, or vice versa. I can't remember which way around I said it. Okay, so that's because there are two different refractive indices. But it turns out that if I've got this in a position so that I'm resolving this amplitude into those two directions where the speeds of light are slightly different, where there are two different refractive indices, then those two packets of light, let's say, travel at different speeds. Now, what I've done here, and perhaps it's running a bit fast, so let's slow the speed down a bit. What I've got here is a simulation. I made the simulation, I'll put it on the comments or on the description of my video a bit later. But I've got two beams, two rays of light, if you like. And these are actually at the same place, but I've split them apart so you can see what's going on. And I can change the wavelength of the light with this slider here on the right, on the left. And the refractive index for one of these beams, I've set it as 2, it's quite high. I'll set the other one as 2.1, so it's even higher, just a little bit, but even higher. So the light gets slowed down more for this beam than it does for this one. So imagine that they have different polarizations. Let's imagine that the red one is polarized vertically. I think I've paused it. And let's imagine that the green one is polarized horizontally. So the light goes through my birefringent material, and as it goes through my birefringent material, like a piece of sellotape, as it goes through there, the component of the light that is polarized in the vertical direction there is going to be going slightly slower than the component of the light that is in the horizontal direction polarized. Right, okay. Now those lights don't interfere, they don't superposition because they have got different polarizations. And actually what's going to happen in this case is we'd end up with a polarization that's somewhere between the two, diagonal, but it doesn't matter. Here we have our diagram where all I've done is added these two together. And the reason I've done that is to help me see when they are in phase and when they're not. Remember, they're not actually going to superposition, but I just want to know what the phase relationship is between these two rays. So what happens as I increase the wavelength? Right now it's on 0.6 arbitrary units. Let's make it it was 0.5, now it's 0.6. Actually, we now get a smaller amplitude. If 0.7, even smaller still. 0.8, it's gone bigger again. So somewhere around here, maybe 6.5, it gets even smaller. 6.4, 6.3, 6.4, 6.5, 6.6, 6.7, 6.8, 6.7, 6.7, 5, 6.7, 3, 2. Okay, so you can mess around with that. Oh, look at that. When it's about a third of these arbitrary units, these two are in, their phase difference is pi radians. They are completely out of phase. Again, they're not interfering with each other, but that's important to know. So the phase difference between these two beams is wavelength dependent. That's important. Now on this simulation, if you want to play with it, it's a Desmos simulation, you can change the thickness, and so you can investigate the effect of thickness. And remember, with my sellotape, there's all sorts of different thicknesses because it's all just screwed up. If you've ever wrapped a present and your wrapping presents is anything like me, you've got these lying around your house. So you can investigate the effect of changing the thickness. You can tweak the refractive indices a bit if you want. It doesn't really matter. It's all there for you to play with. But what I was interested in is what the effect is of the wavelength. So look, a wavelength of one arbitrary unit. Wow, we have them in phase, almost exactly in phase. Right, so let's move on to the second demonstration then. We're happy that the light that passes through the birefringent material gets split into two rays, even if those rays are following exactly the same path, where the electric field for one ray is oscillating perpendicular to the electric field of the other ray, and those two rays travel at different speeds through the medium, depending on the wavelength, so that when they emerge, they could be in phase or out of phase, or some phase difference between them. Okay, fine. I may have misspoken just then because what happens is the optical path length, which is the distance here, in this case it's 10 arbitrary units, multiplied by the refractive index. The optical path length is different for them. And so the reason there's a different phase relationship is because of the wavelength divided by the optical path length. If that's equal to an integer number, then we have they emerge the same phase as they went in. And if it's not, then they don't. So anyway, let's move on to the second little simulation thing. There it is. This is showing us looking down that ray of light. And so remember, the ray of light has gone, here's my birefringent material, light's gone through it, and I'm now looking down that ray. And as I look down that ray, I can see the electric field oscillating vertically, I can see the electric field oscillating horizontally, and right now I've got a particular wavelength, so they're in phase. And if I have my polarizing filter, my second polarizing filter, what we call the analyzing polarizing filter, if I have that in a particular direction, like this, then these two superposition because of the same thing we've just seen over here. It's the same thing. We're adding back the components of the green one parallel to the blue and the component of the red one parallel to the blue. Okay, both those things are happening, and what the analyzing polarizing filter does is it forces us to find the component of the red one parallel to this blue line and the component of the green one parallel to this blue line. And because now they're in the same direction of polarization, we add those amplitudes together. So the amplitude's up here somewhere. There's the amplitude for it. Remember, that's the maximum displacement all the way down to there, up to there. We get this sort of superposition caused by the analyzing filter. But look what happens when I rotate the filter around. So if I take U is the angle of the polarizing filter, and I make it 0.2, 0.15. You can see the phase relationship is changing. 0. Let's make it 0.5. It's not doing that. Let's make it negative 0.25. There we are. Well, now look. I have no component of superpositioned electric field. So I've got my polarizing filter in a certain direction, and so when the red is saying it's along this direction, the green is saying it's along that direction, they cancel out, and vice versa. So they cancel out. We're getting no amplitude. So at that angle of polarizing filter, that's the only thing I've changed, at that angle of polarizing filter, this particular wavelength, which is emerging in phase, is destructively interfered. But at this particular angle, 90 degrees round, that particular wavelength that causes these two rays to be in phase is constructively interfered, reinforced. So this colour, corresponding to the wavelength, is brighter when the filter is in that orientation, but it is darker, it's cancelled out when the filter is rotated through 90 degrees. And this is for one particular wavelength that gives me these two in phase. Remember, that came out of this, a particular wavelength that puts them in phase. But I could choose a wavelength, over here, I could choose a wavelength that puts them in antiphase. So let's look at that. So now they're in antiphase. Whenever the red is negative, the green is positive, and whenever the red is positive, the green is negative. They are in antiphase. And you'll notice that with the polarizing filter, the analyzing polarizing filter, arranged like this, there is no component of amplitude. You add them together, they always cancel out. The red is saying down when the green's saying up. The red is saying up when the green is saying down, vice versa. But if I rotate the polarizing filter around 90 degrees, now this color that gives us the situation we see here, this color can now be seen very brightly at this position of analyzing polarizing filter, but it's invisible in this position of analyzing polarizing filter. And it depends on the wavelength. So let's keep the filter in the same position, and let's just mess around with the wavelengths a little bit, because the wavelengths will affect the phase relationship. And so here we are, there's a different phase relationship between them. We can see that color, and as I increase it, we can see that color, and if I increase it, we'll get to a certain point where we can't see it anymore. But that is much dimmer. It's not completely cancelled out, but the color corresponding to the wavelength that gives us this phase difference causes a smaller amplitude of superpositioned waves when they're superpositioned by using the analyzing polarizing filter. So that color is less bright than some of the others, and some of the other colors are more bright, and so on. So you've got two things going on. The fact that we've got a whole bunch of different wavelengths changing the phase relationship between the two rays of perpendicular polarization planes, directions, but also the fact that we are rotating around our polarizing filter. And as we rotate a polarizing filter around, that changes the components that are added together so that we either get constructive or destructive interference. And those two effects together, it's a bit complicated, but those two effects together are what cause this effect. So if you look where it's yellow, well, yellow light contains green and red, so the blue must be destructively interfered where it's yellow. But you see where it's this sort of cyan color? Well, cyan contains blue and green, so the red must be destructively interfered there. But if I rotate it around, I can now go from having blue down here, or cyan there, but I can make it blue up there, and yellow down here. And I can, get them both to be the same color. We can investigate that relationship between all these variables with this polarizing filter, the analyzing polarizing filter. Last part. Here I have a calcite crystal. Calcite crystals that are very pure, very clear, cost an awful lot of money, a few £100 if you want to get one this sort of size to use in the lab. So I went on eBay and found someone selling magic healing crystals. This was marketed as healing my menstrual cramps, and I can tell you I have not had menstrual cramps since I've had this crystal, so that's something. But here we go. This is a birefringent crystal. It has, because of its structure, different linear densities in different directions, and therefore actually different optical densities in different directions, which causes this birefringent effect. And if I place it like this over this X, and let's zoom right in on this. you can see that there are two, sorry about the condition of my fingers, I've got quite dry skin at the moment, it's winter. You can see we get the two x's following different paths. One of those x's is polarized in one direction, and one of those x's is polarized in a different direction. So let's find a generally clear bit. Let's do that. Let's get my polarizing filter, and I can remove that x that's on the left, and if I rotate, let's put the filter a bit closer to force it to focus. There we are. And if I rotate the filter around 90 degrees, now it's the one on the right. Rotate it 90 degrees, now it's the one on the left. Okay, 90 degrees, one on the right, one on the left, one on the right, one on the left. So we can see that these two rays that pass through this calcite, it's one ray split into two because of the slightly different refractive indices, so the light doesn't follow the same path, but the light that follows each path is slightly different. Well, it is a different plane of polarization, different direction of polarization. And I can see that by using a polarizing filter like this. So there we go, calcite, useful for many things. Also demonstrating birefringence. Hopefully you found that video helpful. That's pretty much everything that you'll need to know about polarization.